Good morning, everyone. We'll get started here today. There's something I want to show you guys in modules and Carmen with sort of like a sample test that we can take just to make sure the lockdown browser settings are working on your iPads. So if you have your iPads here, it'd be great if you go ahead and get those out, and I'll show you how to navigate to this quiz. It's just it's not for credit. It's just something to make sure that your iPad's ready to go for the test. You should have seen an announcement about downloading or setting up some kind of lockdown browser settings. And if you haven't seen that, this may or may not work. If this doesn't work, then you go back and check that announcement. But what we want to do is just navigate over to modules. Your guys' view might be slightly different than mine. Some of these things are unlocked on your view, or locked on your view. And there is under the practice exam preparation, or the preparation for exams, there's like a lockdown browser test. I can actually go into like a student mode here, because I know my view looks different than your guys' view. So let me. Now obviously if you're on the iPad, it looks a little different, but not too much different. So we're just doing this lockdown browser test. So you need a code to begin. The word is just test, all lowercase letters. So when you click on like take the quiz, it's going to pop up, putting in that access code. So when you get to the test, this is pretty similar to how the test will start. Yes? Yeah, let me switch it to the big screen too. And so I haven't downloaded Lockdown Browser, so I would need to download this to begin. I'd actually done this on my iPad earlier, so my iPad was working, and I had never downloaded anything, so I don't know if it was already built into mine. But I think if I leave student view, I can show it to you on this computer. And so there's 3 questions, and the 3 questions are designed just to show you what a multiple choice question looks like, what a data entry question looks like, and what a drop-down menu choice question looks like. And they're all just very basic questions. Let me see if I can preview this for you guys here. So this is actually a decent review question. I don't know how many of you guys have navigated to the quiz. How many of you guys have not gotten it to open and are trying? Raise your hand if you're trying and just haven't gotten it figured out yet. I'll give a few more seconds for you guys to figure it out. Yeah, the code is test. Yes. And so the question was, do you have to access the test through the lockdown browser? I think you'll access it directly through Carmen, and then it'll link to the lockdown browser. So when you get to the test, the proctors will know much more than I know about starting the test, but I'm pretty sure you navigate to the test directly from Carmen. I think you can use the Carmen, the Canvas app. Yes? That has all the instructions. Proctors and all those people know much more about this than I do. And that announcement should have everything you need to know. The reason why they require iPads is because I guess this lockdown browser is quite finicky with different sorts of devices, and so the instructions should be pretty clear for the iPad on what to do. So whether or not you're in the app or not, we can look at a couple of the questions here and kind of see what it is that this particular question here is asking, is this a pure compound, homogeneous mixture, pure element, or a heterogeneous mixture? So what do you guys think? Do we think this is a pure element? If it were a pure element, we'd probably have the same color for representing the same type of atom. So it's not going to be a pure element. If we have a pure compound, we should have one compound, only one compound, not two different forms. So we see what looks like H2Os, maybe it's H2O, but we see two things on another atom, so this looks like a pure compound. And so if we saw, something that had 5 atoms, these things with 2, maybe it would look like some sort of mixture. If we're equally mixed, it would be homogeneous. If we saw phases, it would be heterogeneous. So this looks like a pure compound. The next question is asking for a calculation. Now this question here kind of looks like a sig fig question, and it actually isn't in the context of the way the question's being asked. So this question is just asking us to multiply two numbers, but this is meant to show us what a data entry question looks like. It will usually say to round your result to a certain number of decimal places. It's because the grading system needs there to be a precise number of decimal places in order to correctly grade your answer. And so even if your answer were to be something 0.00, enter the 0.00 into your answer. Even if the sig fig should require an extra digit or a fewer number of digits, you're just still giving the 2 digits that it's asking for. So when we do this problem here, the 2 decimal places may or may not be the correct sig figs, but the question here is asking us to specifically enter that number of decimal places, so that's what we enter. So we do 36.157 times 7.325. So the answer should have 4 sig figs, right? If we're counting sig figs, we would be rounding this to the tens place, but I would write this in as the 5 digits that it's asking for, the 2 decimal places. So first decimal, second decimal. Okay, and so some might say to the nearest whole number. If it said the nearest whole number, we would have said 265. If it said tens place, we would have said 264.9. So just know these data entry questions aren't sophisticated enough to grade sig figs. So these questions here are not grading sig figs. They're just looking for some specific answer to a proper number of placeholders. And then the last question, this is really not worth the review part, because obviously carbon is C, or neon is an E. But this is showing you kind of what a drop-down menu question looks like. So you might see some drop-down menus. Just make sure to answer both parts of the question, or as many parts of the question as are there. And these questions usually go, if there's 2 questions, each of the questions is half a point. So you can get half points if you get one of the questions right. Okay, so I just wanted to walk through that. I know if those who are going to watch this video later aren't seeing what I'm clicking on, but we're just in Carmen here in that modules lockdown browser test. Again, so look at for announcements from Sophie White if your settings are not quite right to get that going. Let me switch over to here. And then I don't want to get too bogged down, because like last time I wasn't going to say as much as I did. I said maybe 3 to 5 minutes worth of stuff on metacognition. I wanted to maybe say just a couple more things. I was planning to go through this a little faster last time than what I did. But again, metacognition is just the awareness of your own learning, your own thoughts. It's trying to understand what topics you don't know so you can go learn more about those topics. Self-assessment is really big within metacognition. If you can self-assess yourself by taking a quiz, figuring out what you did wrong, then you could better go back and learn the things that you need to learn. And so some of the keys of metacognition are previewing material before is always really helpful. Sort of going forward and backwards simultaneously is sometimes helpful too. Sort of moving ahead to the next section in the book, and maybe at some point having to go back to an earlier section on something maybe you didn't understand, that as you go forward and backwards and repeat that process, you may learn things better. So once you see maybe in a given chapter where we're going with some of the concepts, maybe the earlier concepts will make more sense than they would have just in the context of seeing the first section. So you see section 1, maybe it makes sense a little bit. By the time you get to section 6 in the chapter, maybe you can circle back to section 1 and have it make more sense once we complete a chapter. And so that's why I like to go back to review problems in class. I don't always like to just cover the chapter in a linear sequence, because sometimes we need to see something from the end, come back to the beginning, and see problems in a lot of different vantage points to help us learn. Retrieval and space practice are just the ideas of retrieving information as retrieval practice. That's the idea of doing short quizzes or just testing your knowledge. on somewhat of a regular basis. This is why I say closed book, closed note is forcing that retrieval. And then the spaced practice is spacing out the practice. So instead of retrieving all the information in the span of like 6 hours in one study session, having 6 one-hour study sessions throughout a week might be better than that one combined 6-hour session once a week. So having lots of short study sessions, having lots of interval, I think helps us maintain and keep information for a longer period of time. And then, again, self-assessment's huge here. Like if we're assessing ourselves, then we're really in tune with what we know and what we don't know. I think I went through this enough last time. This is just the study cycle of preview, working problems, kind of coming to class, and having a cycle about the learning process. Missing lecture, like in the past, used to be really problematic because you would never get to see lecture again. Now at least you can watch lectures and see videos and things. So take advantage of videos if you need to see something again or if you miss class. But then also make sure to use the textbook in some way. I think at least going through and looking at those self-assessment problems and working in some reading on the ones that are tougher to you. And everybody will have a different set of topics that they personally find trickier than others. Some of you guys might have learned stoichiometry really well, so you weren't maybe reading so much in chapter 3. But maybe some of you guys didn't learn stoichiometry very well. Maybe you don't even remember hearing the word. And so then maybe you needed to do a little bit more review work on that chapter. I think, again, I said almost enough last time on this slide here, is that if you want to get to the upper ends of learning, if you want to synthesize information, if you want to create ideas, if you want to do those sort of things, that's like a senior student in a research lab is going to be creating experiments, synthesizing compounds, generating results. If you want to get to that level, we got to learn the brute force concepts at the early part of a class like ours. So a lot of our class is sort of at the lower levels of the Bloom's taxonomy, but you can't get to the higher level processing part of information if you haven't learned a lot of concepts, learned how to use them, learned how to apply them. And so our lecturers are sort of working on introducing ideas, using them, putting them into practice so that you can get good at doing those things. And our tests, I think you'll see, are at that same kind of level that we're teaching the class at, that our homework problems are at. So I think you can hopefully see that there's a lot of similarity between lecture examples, quiz problems that we've given you, homework problems, and then the ultimate exam problems you'll see like tonight. Those practice exams, the 3 of them, those are old practice midterms. So like students that took those tests always had said those tests were harder than their practice exams. So I'm sure you guys might feel like tonight that the real test is harder than those practice tests. We really try to make the same type of test or the same difficulty level. So I don't think we're trying to make the test any harder. I think it's just the test will always appear harder when we're under the pressure of a test situation. So this slide here, I'll just let you guys look at this. This has a variety of study habits on here that you might think if you're putting these into practice, or maybe see some ideas you might consider putting into practice. I think the big ones to me are just doing a little bit of preview before class and then doing some work in terms of reading after class. These 2 books are really useful here. I think this one to me is the one I prefer. This is the one that my department wants us to mention. But the Make It Stick has a ton of science examples of learning in the context of pre-med students in med school, students on the way to law school, and it has a lot of cognitive science, experimental data that's presented from like a research perspective. So I think it's just a really good scientific book on really like the science of learning. So I think if you were to buy a book, I would highly recommend this book here. Okay, so we had gone through the first few of these problems. So we went through the first few problems last time. I think this was the one we had not gotten to. So let's start with this problem here. So I often call problems that look like this a particle diagram question, where we're given like a diagram that shows us some mixture of molecules. In this case, we're looking at N2s and H2s. And so nitrogen and hydrogen react. So the N2s are the bigger molecules, the H2 are the smaller ones. And so the reaction is 1 N2 plus 3 H2s goes to 2 NH3. And then we're asked to sort of show, based on the initial amounts shown in the figure above, what figure or what is present after the reaction goes to completion based on the theoretical yield. So based on the maximum yield of the reaction. So I want you guys to spend 2 minutes on this question thinking, you have this box here. After the reaction completes, which box is the correct box that the reaction mixture would look like? You guys can chat with each other. Once you think you kind of know the answer, you might convince your neighbor, see if they agree with you. I don't think this is too hard of a question, but okay, is there a consensus on maybe how many of you guys think it's box 3? Do a lot of you guys think it's box 3? So box 3 looks to me to be the right answer, so let's make sure we agree here. So if we take one N2 and 3 H2, so that might be taking these collection of molecules here, then when they react, we're going to produce 2 ammonias in their place, so I'm going to get 2 ammonias. And then when we do it again, we take one N2 and 3 more H2s, and we get 2 more NH3s that form, and then we leave behind the one N2 that's unreacted. And then if we think about the math here, for 6 H2s reacting, they need 1 N2 each. So for 6 H2s to react, I need 2 nitrogens, which would leave behind 1. And then if I were to react all 3 of the N2s, I would need 3 times as much hydrogen. I would need 9 H2s. I don't have 9 H2s. So I definitely can't consume all the N2s, so it should definitely be remaining. And then if I just think of 6 H2s, the limiting reactant, for every 3, I get 2 ammonias. So that would be 4. So if I think of taking the 6 H2s here, for every 3 H2 molecules, we get 2 molecules of NH3, and that, of course, would be 4 NH3 molecules. So the particle diagram questions usually offer a chance for us to do the problem with the picture, with the thought of the reaction in mind, with not necessarily the direct use of dimensional analysis or math or BCA charts. We can still use those tools and put them into practice, and we can still double check some of our math with maybe like a dimensional analysis step. And so box 3 is the right answer for the question. Let's move on here. So this question here, as we get on the packet, we'll get away from chapter 3. I think after this slide, we'll go through some other questions from earlier chapters. But we have 4 chromium plus 3 O2 goes to 2 Cr2O3. So this is just the chromium metal reaction with oxygen. So we're told we have 39 grams of chromium, 16 grams of oxygen. Based on the theoretical yield, this is just a way of saying, assuming you get the maximum possible yield, assuming the reaction goes to completion is another way sometimes this is worded. So sometimes we word this, or the reaction goes to completion. And going to completion just is the maximum possible product yield that we could get from the combination of these 2 masses. Which of the reactant remains and in what amount? So we want to know which reactant is excess and then how much of it is left over. Now, there's a variety of ways we can solve this problem. We could set up that BCA chart, probably not the most popular way to solve a problem. Some of you might go that route. That's perfectly reasonable. Just remember to convert to moles if you're going to the BCA chart. We might, to figure out the limiting versus excess reactant, we might figure out how much product we could make and see which one's less, and that would identify the limiting reactant. Then we'd have to go back through and figure out how much of the excess reactant would react. That's an okay way to solve the problem. Might have a couple extra math steps. What I might just solve here is how many grams of one reactant do I need to react with the other? And then if I get lucky and pick the limiting reactant first, then I don't even have to run through a second dimensional analysis step. So if I just say how many grams of O2 are needed to react with all of this chromium, if chromium ends up being the limiting reactant, I'll see how much oxygen is needed to react with it. It'll be less than the 16 grams if it's a limiting reactant, and I can figure out how much oxygen remains. And so I'm going to consume here all the chromium. So I need the molar mass of chromium. That's 60.00 grams per mole. So it's, 52.00. The 2 sig figs. So it's 51.996, hence 52.00. According to the reaction, for every 4 moles of chromium that react, they need to react with 3 moles of oxygen. So our coefficients in our reaction are mole to mole or molecule to molecule. So that's why I needed to go from grams to moles of chromium, moles to moles of oxygen with the coefficients in the reaction. 1 mole of O2 is the molar mass of 2 oxygens, so 32.00 grams. And so unfortunately, chromium's not the limiting reactant because I get 18.00 grams here of oxygen is required to react with this mass of chromium. So what that means is I have to go through the problem a second time. I was just checking my bag. Usually I have a TI-30 in my bag, and so I just wanted to give the reminder. TI-30, TI-83, TI-84, those are the 3 numbered calculators that are allowed in the test. You can have any model, but with those numbers only. Okay. Okay, so we gotta run through this problem again, just figuring out how much chromium is needed to react with all of the oxygen. So remember, one of the key steps here is the chromium is reacting. So all this chromium is reacting and the oxygen's reacting with it. And so we might think of those steps here when we take our O2, 16.00 grams, 32.00 grams per mole of O2. For every 3 moles of oxygen that react, we need 4 moles of chromium to react with it. 1 mole of chromium, still 52.00 grams. So I get 34.67. Which is luckily, and as it should be, less than 39 grams. I was going to say, like, what do you do in this problem if this is still greater than 39 grams? We would have made a math mistake somewhere. So if you ever see a problem where you're like, geez, neither one of these seem to be the limiting reactant, maybe we inverted one of our coefficients. We might go back and double check that we really did the 3 moles of O2 to 4 moles of chromium correctly. So we could always make math errors. So if you make a math error, I think it's good to be able to interpret, when we do make a math mistake, and we go like double check our numbers and go from there. But 34.7 grams of chromium is the chromium that reacts with this oxygen. And so we had 39.00 grams initially present. So that's the mass that we had initially present. Minus the 34.67 grams that reacted. And so then that difference is 4.33 grams. So 4.33 grams of that chromium remains. So which reactant remains? Chromium. How much of it? 4.33 grams. So the key in a stoichiometry problem like this is always make sure you use those mole-to-mole coefficients from the reaction. If it's at the molecule level, it's a particle diagram, you might be doing a molecule to molecule. We could say 4 atoms of chromium react with 3 molecules of oxygen at the molecular level. So we can apply the equation at the molecular level, so atoms, molecules, units, or we can apply it at the mole level, so 4 moles of chromium to 3 moles of oxygen. Okay, actually I think maybe after this question we move out of chapter 3, but this is a good review problem to look at here. One of these problems here, like this one, of analyzing a sample that contains CH and O. And this could be a different element than oxygen, and I'll show in the problem what we would do differently if this were something other than oxygen. And then we're told how much CO2 and water it produces. And so this is often called a combustion analysis problem. So we're analyzing a pure compound that we know what elements it's comprised of, and we're analyzing how much CO2 and water are formed from the reaction of the compound, because all the carbon goes to CO2, all the hydrogen goes to water. And from those masses, we can work out how much mass the C and H the compound has. And then by simple difference, we can work out the third element, how much mass it has. And then we just have to know what the third element is. So when we're going from the mass ratio to the mole ratio, we know what atomic weight to use. And so what I would do in this problem here is I would work out the number of grams of carbon and CO2. Then I'd work out the number of grams of H in water. I'd start with the 14.08 grams of CO2. Now there's a few ways to do the problem. Let me do the problem the way I haven't done it, just in case. This is the way that I think the book shows it. I have a slightly simpler way of getting to the equation that we're going to multiply this by. But the book kind of just goes grams to moles, so 44.01 is the formula weight of CO2. So it uses the molar mass of CO2, and then 1 mole of CO2 contains a mole of carbon, and 1 mole of carbon has a mass of 12.01 grams. So pretty easy conversion, just grams to moles, moles to moles of carbon, molar mass of carbon. And so then let me show you how I've shown it before, just as a reminder for water. And how I showed this before is, if you want to know the mass of just hydrogen in water, we know the percent H equation. We know how to calculate the percent H in a compound. Just multiply the mass times the percent by mass of the element in the compound. So all we really need to do is multiply this by the percent H in water mass, the percent of H by mass in water. And we know that this is equal to 2 times the 1.008 molar mass of water, divide by the molar mass of water. And so we can just multiply by the percent H mass. So the percent hydrogen in water is just 2 times 1.008 times, divide by 18.02. So I didn't multiply by 100, but in a fraction it's 0.1118, so it's 11.18% hydrogen by mass. I'm just multiplying that fraction by 4.32. And so for hydrogen, it's 0.483 grams of hydrogen. And so now we could go grams to moles, moles to 2 hydrogens atomic weight, like we did for carbon. Or we can just say it's 4.32 times the percent H in water by mass. And we know that equation from earlier in chapter 3. And so if we go through and calculate the carbon mass, 14.08 divided by 12.01, 14.08 times 12.01 divided by 44.01. So that's 3.84 grams. And so the key is that the sample that contained all 3 elements was 12.01 grams. And so the third element, the mass of water, the mass of oxygen, is the 12.01 mass of the sample that had all 3 elements, and then minus the mass of hydrogen, and minus the mass of carbon. So that's 7.69 grams. So if I know this is the mass of the elements in the compound, then I can get to the ratio of the moles just by dividing by their atomic weights. Let me zoom in a little so the pen goes back to a normal size. So we're going to use 12.01 grams per mole of carbon, 1.008 grams per mole of hydrogen, and then if we have whatever the third element here is, we're using its atomic weight. So if this were nitrogen or sulfur, we're just looking up and using the atomic weight of that different element. But for oxygen, 16.00 grams per mole. So here you're using the molar mass of the elements. So 0.320. Somebody woke up early today. because they're here. So the first one was moles of carbon, moles of hydrogen, and then for oxygen, 7.69 divided by 16, 0.480, 0.480 moles of oxygen. Okay, and so then the next task is divide by the smallest. So just find whichever of these is the smallest quantity, divide all those by the smallest amount. At least gives us one whole number. And so we get our ratios 1 mole of carbon present to a ratio 0.480 divided by 0.32 is 1.5. So 1.5 mole of oxygen. So these would be the ratios for the particular sample that we've worked out here. And so the 1 to 1.5 to 1.5, we need to think, do we need to multiply by 1? 1 doesn't work. What about 2? So if we double all these moles here, then we get the whole numbers. So our ratio is going to go from 1 to 1.5 to 1.5 for C to H to O. We're going to double all these to 2 to 3 to 3 to get the whole numbers. So our empirical formula should be C2H3O3. And so then the problem is looking for that empirical formula. Sometimes the problem might ask for a variety of things. It could say if, I'll get to your question one second. So the question might say, which molecular formula is consistent with this data? Like that's a variation, sometimes it's been asked of this problem. And then you'd be looking for the molecular formula that would be consistent with this empirical formula, is one variation. Another variation is they give you the molecular weight, and then you find the molecular formula by finding the number of multiples. So if we know the empirical formula of this is X, the molecular weight's 4X, then there's 4 units of this in the empirical formula. There was a hand over here. Oh, okay, yeah, good question. So the O2, so in a combustion reaction, we know that you're taking, like your hydrocarbon plus O2 and generating CO2 and water. And so the oxygen in the sample is going, some of it into the CO2, some of it into the water. And then we're taking external oxygen to give us the rest of the oxygen. And so, yeah, we never really know how much extra oxygen's added in. Yeah, so there's excess oxygen to produce the products. And then the actual oxygen's coming from both that external source, the one in the atom. So, but the key is that all the hydrogen goes to water. There's no other product hydrogen goes to. There's no other product that the carbon goes to. So all the carbon ends up as CO2. All the hydrogen in the sample ends up as water.
So when you were finding your formula, they were asking us for molecular formula. We have to know molecular weight of substance.
Yeah. And so like I said, some variations of the question will say which molecular formula is consistent, where they're not really saying that is the molecular formula, but just it has the right empirical formula.
And that would just be like the same ratio.
Yeah. And so, there's always like a few variations, but just make sure, so the last part that I went to in the question was I went back to very, carefully try to see what's the question actually asking for. Because sometimes in a problem like this, you think it's asking for empirical formula, and it's actually not. So just go make sure you double check once you finish a problem like this, especially on a problem like this where you think you see the numbers and you start crunching the numbers. Once we ask for what's like the percent O in the compound. So the percent O in the compound would actually be, once you get the mass here, once you know that it's 7.69 grams, the percent O would just be that mass of O divided by 12.01 times 100%. And it's kind of funny that asking the question that way we thought was helpful because then you don't have to do this step here. Like you don't have to go through then and figure out the ratio of the moles, so it shortens the problem. But then students still did that, and then we're still trying to figure out, once they got the formula, how to get the percent O. So unfortunately, students didn't see our shortcut that we had intended them to do, so it kind of backfired. So I don't think we'd ask that again, but the CO2 I went through and just did it a different way, just to show an alternate approach, and it's like the book approach. I would just want to make sure that I linked the way that some other problems show how to find the mass of carbon. But if you notice that we could take this here times the percent C and CO2, and the percent C and CO2 is 12.01 grams per mole for the one carbon, 44.01. So the math is the same. So it's still 12.01 divided by 44.01. You can get there two different ways. Yeah, so it's just an alternate approach that gets you the same approach. And so I suspect people have seen this problem worked out this way somewhere else before. Maybe a TA showed it that way too. I just wanted to make sure that we saw that there's more than one way to solve that problem. Yeah. Okay. So one of the questions I sometimes get is those opening experiments in chapter 2, what do you need to know in terms of the cathode ray tube experiment? I would generally know the name, the discovery, and just maybe like a one-sentence description, not much more than that of the experiment. Like the cathode ray tube experiment put a high voltage and saw a subatomic particle that was found to have a negative charge. It was the discovery of the electron by J.J. Thomson. The next experiment we talked about was the Millikan oil drop experiment. That was the experiment where you were putting charges on a droplet and suspending the droplet with electric field. So that was discovering the mass and charge of the electron. So it was creating the electron or the charge on a particle that you can then use the electric field and gravity to counterbalance and figure out the mass and charge of the electron. Curie discovered the radioactive pathways, the alpha, beta, gamma rays, where the beta ray was the electron, the alpha particle was a helium nuclei, or like a heavy positively charged particle, and the gamma ray was just a high energy packet of energy. I think the main idea here is understanding that that experiment produced the particle, the alpha particle, that was used in the Rutherford gold foil experiment. So I think the real take-home message for why we talked about the radioactive pathways of matter is just so we can understand what the alpha particle was, or that it was some collection of positive charge. So it was a positively charged, relatively massive particle. At the time, I don't think they knew it was a helium nuclei. They just knew it was kind of like the electron, but more massive, but positively charged. And so then they took that particle and intersected it with a piece of gold foil, and they thought it would just go right through. And it turned out it didn't go right through. A lot of the particles bounced backwards, and that led to the nuclear theory of matter. And so that led to the proposal and then the description of the nuclear theory of matter, where the positively charged particle, the proton, and then ultimately later discovered the neutron, accumulate in the nucleus, and a really compact nucleus where most of the mass of the atom is. The electrons contain almost no mass at all, but a really low mass, and they're spinning outside the nucleus. And so, and if an electron hits that alpha particle, the alpha particle goes right through, but if it hits a nuclei, it's going to bounce backward. And so the nuclei was massive enough to cause what ended up being a less massive helium nuclei to bounce backwards in their experiment. And so what would happen if you used a thicker sheet of gold foil? Do you think more particles would bounce back at you, or more particles would go through the metal? And I think it's not a trick question. If you use a thicker piece of gold, more particles are going to come back at us. So we're going to see more backscattering. So more particles would be scattered at large angles, or more particles would pass through the foil. We're not going to get more particles through the foil. We would expect a change. We would expect more particles to be scattered. So more particles scatter at large angles. So large angles are large angles backwards. So think about this angle to the angle it deflects back. So that's what they mean by large angle. So it should have went right through, but it came back, so that's the large angle. So straight through versus where it was scattered. And so we're not going to get more particles through the foil and scattering, so that doesn't make any sense that we're going to somehow have both more particles get through and backscatter. We're going to get more backscattering. So this statement here doesn't make any sense. Okay, so this problem here, so with no given conversions, like the one conversion that goes from a length unit in meters or some type of length unit to volume, the only one that I would expect that we all know is that 1 cubic centimeter is 1 milliliter. So this is the only conversion I think that we need to know to solve a problem like this. So if we know this conversion here, then we can convert dimensions from cubic meters into cubic liters. Now let me solve this problem two different ways. Let me do it the relatively, like the simpler way to get the volume, but the harder way to do the conversion. So if we just take the dimensions in meters, and multiply them together. So 5 times 8.5 times 2.5. I get 106.25. Those are all sig fig quantities, so this should have 3 sig figs here. So this number of cubic meters, I'll keep the extra decimal places around. If I'm converting this to liters, I could do this from this step here, I think, 2 ways. I could either, one, know the direct conversion by memorizing it, and some of you might know the conversion. You can use it if you know it. I usually forget it, but I think it's 1 liter is 0.001 cubic meter. Okay, if you know that conversion, you can use it directly. But the way we would go about this problem if we didn't know that conversion, if we're trying to convert this into liters, I would take this number of cubic meters and I would use the conversion 1 meter is 100 centimeters. And the reason why I do this conversion and I end up having to cube it is because I want to use this conversion here that I know. That gets me from the cubic length unit into the liter, or some type of liter unit. And so the key is I have to cube the entire conversion factor because I need to have cubic meters here and I need to get cubic centimeters, so I have to cube the 100. So 1 meter by 1 meter by 1 meter box would be 100 by 100 by 100 centimeters. So I just have to make sure I multiply this by 100 cubic centimeters, or 100 cubed, centimeters cubed. And then I can use a conversion that 1 cubic centimeter is 1 milliliter. And of course 1 milliliter, or 1,000 milliliters, or 1 liter. So we're taking 106.25 times 100 times 100 times 100, that's 100 cubed, and then dividing it by 1,000. And so that gets me 250 liters. And so if I'm expressing this answer in scientific notation and rounding it to 3 sig figs, I would go 1.06 times 10 to the 1, 2, 3, 4, 5. So we'd be going with answer C. And so the only thing I would make sure is make sure this step here, we're putting this into the calculator correctly. So this is either 100 caret 3 or just literally 100 times 100 times 100. Now, I mentioned that there's a second way you could approach this problem, which is just convert all these to centimeters before you do the volume conversion. Then we get rid of that cubic conversion step. So just convert all if we convert these to centimeters, we'd have 500 centimeters times 850 centimeters times 250 centimeters, right? Because there's 100 centimeters in a meter, so I'm just multiplying all those by 100 centimeters per meter. And so that gets me 106,250,000 cubic centimeters. And so once we work out the volume here, this would be I'll write it out full, cubic centimeters. And so this is just coming about from converting the meters to centimeters before we do the volume calculation. And look, I actually avoided having to do this cubic conversion step because I kind of converted to the centimeters already. And so then all we need to do is realize that's a milliliter and then divide by 1,000 to go to liters. So if we divide this by 1,000, we get 1.06 times 10 to the 5, rounded to 3 sig figs liters. And so a problem like this, with the cubic centimeter conversion, there's usually a few different ways depending on the way the information is given. If you can somehow convert to centimeters first, you save yourself the possible mistake of missing the cubed here on the 100 cubed. And so what happens a lot of times I see on tests on a cubic conversion where you need to convert cubic meters to cubic centimeters, a lot of students will just do 1 cubic meter. They'll use this conversion. 1 cubic meter is equal to 100 cubic centimeters. You can see how that's nowhere near correct. So a lot of times we miss this 3 here. And if you have some way of avoiding that conversion step, you might miss that mistake in the problem. So this approach here might be good if we want to avoid that slightly trickier cubic conversion step. All right, let's look at a sig fig question here. I actually vividly remember still the semester we gave this question, and I think it's in some parts a dumb question, but it's almost it kind of is a trick question. So let's just look at it. So we have some number of centimeters minus some other number of centimeters times some centimeters here plus centimeters. Now, the thing you have to understand in a problem like this is that we're trying to trick you. I don't want to trick you, but whoever wrote this question was trying to trick their class. like you would imagine that if you were measuring the length of an object, that you would have the same placeholders. Like you would probably imagine you took the same ruler to measure this object, and then if you came up with 1163 for one object, how is it you would only have 20 for another where you didn't know that this 0 was significant? So when you look at 20 centimeters here, the hard part is just realizing that you just almost have to imagine 4 different tools were used to measure these different lengths with different precision. So maybe this 20 was just some object's length was measured with a really bad tool, and then it was only known to 1 sig fig. So I think the part of this question that tricked most students was, how is this, if this is good to the 1's placeholder, isn't this value as well good to the 1's placeholder? And the answer is no, unless we're told more information. So unless we were told that was 2.0 times 10 to the 1 centimeters, or we were told maybe with an underline, which we usually don't use, or maybe with a decimal point, if we were told this, usually that's the implication of 2 sig figs. Or if we have this underlined, or if this is 2.0 times 10 to the 1, those are all the ways we would express 20 correctly with 2 sig figs. Otherwise, I'm interpreting that 20 as just having 1 significant figure. So the issue here is 20 only has 1 sig fig, so when I do 20 plus 1163, that this is getting rounded to that 10's placeholder. So this result here would only be good to the 10's placeholder. So if I was reporting just the result of that second addition step, I would round that to 1180. Not quite in here. So 1180 would be how I would round that second step. Now sometimes confusing, I would usually keep 1183 in the calculation and then just the memory that it's the 10's placeholder, that's the last digit that's significant. So then if we do the next step, so we follow our order of operations, 11.160, let's line this up, or excuse me, 15.160 minus 0.00063. So this is how those digits line up. It is like eerily quiet in here. It's like the spirit of the class who missed this question and like 15% of the class got it right that's interrupting us. So 11.151, and then the extra digits here would be 37. Yeah. And so we'd be good here to the digit of 1. So we'd be good here to 5 sig figs. So if we're reporting the second step here, I'd report the first step, the second one that we did. I'd round this to 15.151. And so then when we're multiplying these together, we can either multiply them when we had rounded, or we can go back to the 11.15137 times 1183, and just know that this digit here was only good to 3 sig figs. And so when I take 3 sig figs times 5 sig figs, it's actually not even asking for the numerical answer. So it doesn't quite matter how you had done the math step to get the final answer, but the final answer would only have 3 sig figs. Because when we're multiplying here in the final step, we have 3 sig figs times 5 sig figs. So the correct answer here would be 3 significant figures. Now let me say one thing, I'll take your question 1 second. So the key is 20 has 1 sig fig. 1163 has 4 sig figs. You may have looked at this problem and said, well, why is the answer not 1 sig fig? If we're multiplying and one of the values has 1 sig fig, why is it not 1? The answer is that it's not 1 because we have to look at the 20 plus the result of adding 1163. And so that step there is good to the 8's placeholder. It's good to where the 20 was good to, just the 2. So the hard part here is recognizing 20 only has 1 sig fig, not 2. And then the result of adding it to 1163 gives the result 1183 only 3 sig figs. Question back here. So yeah, so if the problem instead were say 25 plus 1163, then it's just different because then we know we have 2 sig figs. So it's at 0. It's that whenever you see a number like 100, that you have to assume it only has 1 sig fig unless you know something about those zeros that only the 1's significant. Now, if you do a different context of a problem, if you have 25 grams plus 75 grams, you get 100 on your calculator, that's a different context. That's 100 with 3 sig figs. So if you know something about the zeros, they might be significant, But if you're just shown the number 20 in a problem, the implication is unless you know by notation or some scientific notation used, you're assuming just one sig fig. Yeah.
I know that it's not one sig fig, but what addition and subtraction rules for sig figs with decimal places?
So it's the, well, you can think of decimal places. I think you can call this a decimal place. It's just like the positive decimal place, or it's on the left side of the decimal place. So you might call it a placeholder. So what really matters in the rounding of a problem is the placeholders of the last digits that are significant, and we're always rounding to the greater value. So the greater value of the last significant placeholder, which is the tens placeholder in 20. So you're just looking at a number. Let me get rid of this here. So if you have 20, 1163, again, you're just kind of underlining the last digit of significance and then rounding to the placeholder that's greater in value. And so hence, 1180 is how we would report that result if we were just reporting the result of that second addition step.
So if it was 2,000 plus 1,100, it'd still be the
Yeah, let's do that one. So if we said it's 2,000 instead of 20 plus 1163, then we would assume here that some other tool that was used to get to 2,000, it's some other estimation, so it's only 2,000 plus or minus 1,000. Really weird number, but we would call this just 3,000. It's like, the analogy is like we had used this before. If you have approximately $2,000 and I give you $10, you still have approximately the amount you thought you had originally. The $10 is enough to change your estimation. It's like, how well do you estimate a value? The better you estimate it or know it, the more precise we can be with our calculations. Aluminum oxalate has the formula here. So oxalate's not from our nomenclature, but we can tell you, like if you know aluminum oxalate has this formula, you can work out that oxalate has a particular charge. Because we know aluminum's a 3 plus, so there's 2 of them, total of a 6 plus from the oxygens. We have to have a 6 minus from the 3 oxalates. Do you see how we can work out that the charge on oxalate is -2? So by knowing what aluminum oxalate is in terms of a formula, we can deduce the charge and the identity of oxalate as C2O4 2- is oxalate. And so then we can ask you a variety of questions. We can say, well, what would oxalic acid be? What would the formula of oxalic acid? Oxalic acid would be H2C2O4. I don't think it would exist, but if we said, well, what would oxalous acid be? You just go one oxygen fewer. So oxalous acid would be H2C2O3, because losing an O changes us, or the ate to ite, and the acid name from ic to us. You could say, what would the formula of iron 2 oxalate be? So iron 2 oxalate is just iron 2 plus paired up with the C2O4 2- ion. So that would just be FeC2O4. So we can give you like a name where you can deduce the charge and formula of some anion and then systematically name other compounds based on that nomenclature. A bunch of names here, like I don't know if we have time to get through all of these, but let's look at some of the more interesting ones. Hydrogen phosphite is adding H plus to phosphite ion. So 1 H plus to PO3 3- gives us HPO3 2-. And so then if we have the aluminum cation paired up with this with the 3+ charge, then we're going to need 3 of the hydrogen phosphites, 2 of the aluminums to balance out their charge. So aluminum hydrogen phosphite would be AlHPO3, 3. So HPO3, 3 for the phosphite. Chromium 6, just remember chromium 6 is the charge of 6 plus, oxide's a 2-, so this is CrO3. Let's just do the peroxide. We'll end with this one here. The peroxide, this is cesium peroxide. How do we know this is peroxide? I know cesium is a plus, so it's in the it's in the sodium group, alkali group, so it has to have a plus charge. There's 2 of them, so I have a 2+. So my entire group of 2 oxygens has a -2 charge. And the name of 2 oxygens with the 2- charge systematically is peroxide. If we had CSO2 without 2 cesiums, this is now plus, this is now minus, this is cesium superoxide. And so we can have peroxide, superoxides. Now keep in mind that peroxide and superoxide only form with alkali and alkaline elements. They're not forming with transition metals. So they're a pretty rare compound. You're not going to see these sort of compounds pair up with something like titanium. So titanium is just your simple oxide minus 4. So TiO2 would just be titanium 4 oxide. All right, that's our time for today. All of these are from quizzes or other exam problems that have video keys, so I don't think there's any problem here that doesn't have a video solution somewhere. But if there's any questions on this packet, office hours later today, send me an email. Good luck on the test tonight. See you guys on Friday. Here in the syllabus. I'm back in my office after class, just going to go through the rest of the answers on this activity. So our next molecule, H2SO3, I come to H2SO3 being sulfite. So this would be ite to us acid. So I'm recognizing this as the acid form because I have hydrogens added in front, no charge. So we name this as being an acid. And then this is going to be sulfurous. Now, we don't really test you on spelling. Like there's no data entry questions on typing in a name, so you're just picking these from the name. So sulfur, OUS acid. And you get a space between the name and acid. Recognizing what this is, like in terms of is this some sort of an acid? It's not. This looks like methane with the OH group added in. So this is methanol. So this is the alcohol of methane. This is not an alcohol here of some hydrocarbon. This is the carboxylic acid. This is acetate ion. So that's acetate. This is acetic acid. A more recognizable formula right now is probably giving HC2H3O2. This might be more recognizable at this point in the class to be acetate ion, but we could also more explicitly write it out as CH3COO minus. So if you notice CH3COO minus would have this condensed formula. And so we could write two different formulas for acetic acid. Muriatic acid might take a second to realize this is per iodic acid, per iodate. Iodate is IO3 minus, per iodate therefore is IO4 minus, acid form 1H plus, HIO4. And then nonanol is the alcohol of nonane. Nonane is the 9 carbon isomer, so we have 9 carbons, C9. It's going to be H20 for nonane, so H19OH. C9, H19OH. Now, you might be wondering, how do you know nonane had 20? How do you know nonanol has 19? Well, I'll just have 9 carbons here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Put CH3s on the end, CH2s in the middle, and count. What you should end up with is CH3s on the end, 7 CH2s in the middle, and that's CH3 on the end. And so that's 14 plus 3 plus 3, so that's 20. That's how we got to the 20 in nonane, and then we're just replacing any one of these H's with the hydroxyl group. We're not worried about the numbering system, so just replacing one H with the OH group. So the formula C9H19OH, you could also call it C9H20O, but that's not as common. You can write it condensed or descriptive. Subatomic particle, who's discovered the electron, that's Thomson. Late 1800s, subatomic particle was discovered first, that was the electron. The last particle is the neutron. The neutral particle, harder to discover. What particles did Curie discover? The radioactive pathways, the alpha ray, the beta ray, and the gamma ray. High energy light. Beta ray was the electron, alpha ray is the helium nuclei. Let's look at some more sig fig problems. We have 50 plus 74. Here we're given the result the proper number of sig figs, assuming all the values are inexact measured quantities. And so here we're just assuming these are all the numbers that have the rules of sig figs associated with them. So 50 would be 1 sig fig, 74 would be 2 sig figs, but we're looking at the placeholders or the decimal places, showing somebody this after class that we can express any number in scientific notation. 50 in proper scientific notation would be 0.5 times 10 to the 2, whatever the unit is. And so this would equal 50. That's another representation of 50. So the number 5 is still a decimal place. You might call it a placeholder if you prefer, but it's still something I look at as a decimal place. And so we're looking for the greater value placeholder. So we have the ones versus 10. So we round this to be 120, which ends up having 2 sig figs, but to the tens placeholder. So again, it's all about 50 to this placeholder, 74 to this placeholder. We're rounding to the higher value. Next operation below, we have 16 times 1.25. So this result here would be good to 3 sig figs. And then we're dividing it by the sum of two numbers, which 1.25 plus 3.75 looks like that'll have 3 sig figs still. And so that'll be 5.00, but with 3 sig figs. So when we do this math here, the end result should have 3 sig figs. So I'm just going to do 16.0 times 1.25. So I get 20 on my calculator. So it's really 20.0 if we were noting this down. 3 sig figs, and then divide by 5 would go to 4.00. 3 sig figs divided by 3 sig figs, we keep all 3 sig figs. This value here, this is slightly a tricky problem with the scientific notation, but not that tricky because what I might do is just write these out explicitly. 4, 7, 4, 0, 0. So that will be times 10 to the 1, 2, 3, 4. And then if I add to that 787, 0, 0 is this number just written out explicitly. You see that we have the hundreds placeholder plus the hundreds placeholder. So 47400 plus 78700 should be good to 126100. So this result here, I could write this 12.61 times 10 to the 4. If you notice, if I had 4.74 plus 7.87 in a different context, just as numbers, that this would be 12.61 with 4 sig figs. And we still get 4 sig figs when we have times 10 to the 4 for both of them. So this is 4 sig figs. And you can also express this as 1.261 times 10 to the 5 is another valid way of representing that number. It's 1, 2, 3, 4, 5 is now the number. Now, some students look at this and say, well, if this was tens place, if 4.74 was good to the hundredths place, 7.87 is good to the hundredths place, why aren't we rounding to the 6 to the hundredths place? And the answer is that that's wrong, that approach is incorrect because we changed the exponent. So you can't change the exponent. You got to use the same exponent. You can see 12.61 times 10 to the 4 would be the proper answer to 4 sig figs, just like 4.74 plus 7.87 is good to 4 sig figs. Once you see that it's 12.61 times 10 to the 4, then you can move it to 1.261 times 10 to the 5 if you want to express it in the exponent times 10 to the 5. All right, so let's take a look at question 23 here. So hydrogen gas and oxygen combine to form water. H2 plus O2 goes to 2H2O. After the reaction is complete, I have 6 moles of water that's been produced. 4 moles of oxygen remain based on the theoretical yield, or assuming the reaction goes to completion. How many moles of gas were initially present in the container? Okay, now I can tell you that when this question was written, whoever wrote this question was thinking of a BCA chart. So let's start there, and then after we see a BCA chart, I'll go through how you can solve the problem without a BCA chart. Okay, so what I might look at here is that after the reaction is complete, I have 6 moles of water. So I initially had none. So reaction begins. I just had reactants. So I have a plus 2x, and I know this is going to 6 moles. And so I have 6 moles of product here. Then that should tell me that x is equal to 3. I can solve for 3 moles right off the bat. And so then I'm losing x, and I'm losing 2x off of my reactants. And I don't know how much of these I initially had to begin with in the problem. I just know that after the reaction is complete, so after I produce the 6 moles of water, I then have 4 moles of oxygen remaining. And if the reaction was to completion, I have none of the H2 left at the completion of the reaction. And so then if X is equal to 3 moles, then if I have 4 moles of oxygen left, it means I had to have originally had 7.0 moles of O2. That's 7 moles of O2, so I could lose 3x, or lose 3 moles, which is X, to get the 4 moles. So let me say this again. If I know that I end up with 4 moles of oxygen after the reaction is complete, and I know that 3 moles of oxygen had to be consumed to make 6 moles of water, I therefore had to have had 7 moles of oxygen initially present. 7 initially present, 3 of them reacted, 4 were remaining. And so then how much hydrogen had initially been present? Well, 2x had reacted, so x was 3. So I had to at least have 6 moles of H2 initially present, lost all 6 moles. For every 2 moles I lost, I make 2 moles of water. So it started with 6 moles of H2 and with 6 moles of water. So minus 6 moles here, 2 times x, down to 0. So I initially had 13 moles of the reactant H2 and O2 present. So how many moles of gas were initially present in the reaction? The key that I have to know that I think is a little bit tricky to know is that we're starting with reactants, so we didn't have any of the product yet present initially before the reaction took place. I'm using the coefficients, losing the reactants, gaining the products, so gaining, losing, getting my x relative to each other, and then solving for x with the water right off the start, and then adding up the initial reactants to solve for 13 moles of gas. And so another way I can do this problem is just dimensional analysis wise by kind of realizing that I can say things like, well, how many grams of H2 were required to produce the 6 moles of water? Why writing moles so hard for me sometimes? I write too fast. So 6 moles of water. For every 2 moles of water that are produced, we had to start with 2 moles of H2. So 2 moles to be produced, 2 moles of water had to be consumed. So I'm consuming 6 moles of water, or 6 moles of H2 to make 6 moles of water. And so then I have to then realize that, again, if this reaction hit completion, all this H2 is now down to 0. So all this H2 that was initially present is now gone. Otherwise, the reaction would have kept going because I have oxygen present. So my H2 after the reaction goes down to 0. So this much reacted, this much was initially present, down to 0. But the key is I had 6 moles initially present. And so then if I want to calculate the number of moles of oxygen, I started here number of grams, this should be number of moles. I'm just keeping everything in moles. O2 moles of hydrogen. The number of moles of oxygen that had reacted to produce the 6 moles of water, this is where we use the 2 moles of water being produced, require the consumption of 1 mole of O2. And so this is going to give us 3 moles of oxygen had reacted. And so therefore, if 4 moles are left over after, so if I have the X as the initially present, minus the 3 moles that had reacted, equals the 4 moles that are present in excess, that X has to be equal to 7 moles. Let me come back to something on this hydrogen that I think that wasn't entirely clear. So let's come back to this step here, because I want to contrast real quick. So when I calculated here, I got 6 moles of H2. 6 moles of H2 had reacted. And I knew I got down to 0 after the reaction was complete. And so then, in order to get down to 0 meant that that's how I knew 6 moles of H2 had to be initially present. Okay, I was making it seem like the 6 moles that we had found by calculation was the amount that had to be initially present, but it was really from the thought of H2, none of it being able to be left over after the reaction was completed, to us knowing that therefore 6 moles had to initially be present. So 6 plus 7 is equal to 13. So dimensional analysis, VCA chart gets us towards the right answer in number 23. Particle diagram here, Cl and O2, or excuse me, Cl and F2 reacting. It doesn't matter which are which here, because you have 6 of each. You have 6 molecules of F2, 6 molecules of chlorine, and so it doesn't matter which is which. But I'm going to identify the gray spheres as Cl, the dark spheres as F2. And so then the reaction that's taking place is forming chlorine trifluoride. Okay, so we have to think about nomenclature here. So Cl plus F2 goes to ClF3. So we're going to need a 2 here for 2 chlorines, and then we're going to need a 3 here for 6 fluorines on both sides. And so for my F2, I need to take 3 of my F2s, just 1 Cl2, something like this. Then I get 2 ClF3s that result from that. 2 ClF3s from this collection of molecules now being reacted. And then I can do this just one more time. So again, 3 dark spheres, 1 of the gray spheres. So I get 2 more ClF3s. So I'm going to get a total of 4 ClF3 molecules in total. And then 3 Cl2s left over. So the question, what's it asking? Which statement is true? 2 molecules of fluorine remain, all the fluorine is consumed. Incorrect. 4 molecules of fluorine remain, all the fluorine is consumed. That doesn't sound right. 2 molecules of chlorine remain. Oh, no, actually, that's 4 molecules of chlorine remain. I miscounted here. So there's 1, 2, 3, 4. So 4 molecules of Cl2 remain. All the fluorine's consumed. Now you can double check. You can say 6 F2s, for every 3 F2, we need 1 Cl2. So obviously that's 2 Cl2 molecules that are needed, and we had 6, so 4 left over. Aspirin, reaction, yield. So aspirin's prepared by the reaction here. Everything's 1-to-1, the reaction's balanced. The massive C7H6O3 then must be reacted with excess of this reactant here to produce a yield of 1 kilogram of aspirin, but if the yield is 71%. So we're trying to make a kilogram of this, but we know we're only getting 71% yield. So based on the percent yield, we actually want to get 1.0 kilogram. The theoretical yield we need to shoot for is therefore going to be higher than a kilogram. So I've just gone from 71% to the ratio of 0.71. And so my theoretical yield I need to shoot for is 1 kilogram divided by 0.71. I like to think of the analogy. If you want to make $1,000 a week take home pay, you need to really bring home about $1,400 a week. So that once you get to keep 71% of your money, you get the proper amount. So the same analogy here applies. The theoretical yield that we need to try to make is 1.4 kilograms. And the only thing we might do is recognize that's 1,400 grams. If we carry an extra digit, it's 14.08 grams with the 2 sig figs. And so then I might be going through this process here, trying to figure out the number of kilograms of a reactant. I could have left it in kilograms, but I like converting to grams. But the number of kilograms of C7H6O3 would be equal to 1408 grams of the aspirin times the molar mass of aspirin. So I have to calculate for 9 times 12.01, 1.008 for hydrogen times 8 plus 4 times 16. So that's a molar mass of 180.2 grams per mole of aspirin. 1 mole of aspirin is produced from 1 mole of C7H6O3. And then the um, molar mass of C7H6O3 is 12.01 times 7 plus 1.008 times 6 plus 16 times 3 is 138.1 grams per mole. And this is, of course, backwards. So we want the mole in the denominator, so we want 138.1 gram per mole of C7H6O3. So this cancels, aspirin cancels, gram cancels. And we're just doing 1,000 grams is a kilogram. 1408 times 138.1 divided by 180.2 divided by 1,000 is 1.1 kilogram. Protons, neutrons, electrons, iodine 127 with a minus charge. Now remember, you can't always predict this number just looking at the atom, but we can predict the atomic number, which would be the subscript. So the atomic number is 53. This comes from, of course, the periodic table. This is the number of protons in the nucleus. 127, the mass number, is the sum of the protons plus the neutrons. So 127 minus 53 is equal to the number of neutrons. So that's going to be 74. And then the number of electrons, we have one extra electron, 54 electrons. So C looks good. 53 protons, 74 neutrons, 54 electrons. How many oxygen atoms are present in a 6.50 gram sample of CO2? We're going to take the approach of grams to moles to atoms. We use molar mass here, or we're going to use Avogadro's number to get from here to here. And we're going to need to use a formula at some point of the way too. Okay, so 6.50 grams of CO2, 44.01 gram per mole of CO2. 1 mole of CO2 contains an Avogadro's number of CO2 molecules. And then one individual molecule of CO2 contains 2 oxygen atoms. So we get this from the formula. We get this from knowing Avogadro's number and what it means. We get this from the molar mass. 6.5 divided by 44.01 times Avogadro's number, 0.022 E23, and then times 2. This is 2 oxygen atoms on 20. So this is 2 oxygen atoms per CO2. And that's 1.78 times 10 to the 23. Last question on the packet. We know percent C, percent H, and the molecular weight. What is the formula? The way I would approach this problem here is start with the ratio of masses we know to be true for this compound, 87.7 grams of C in ratio to 12.3 grams of hydrogen times 12.01 grams per mole of carbon times 1.008 grams per mole of hydrogen. I think this is just CH, but we'll see in a second. 7.30 moles of carbon are present in ratio to the sample for every 12.3 divided by 1.008. This actually isn't going to be CH. 12.2 moles of hydrogen. So we started with a ratio of masses. Now we get a mole ratio. We just need the simplest whole number ratio. 12.2 divided by 7.3 helps us get there. And so if I divide by the smallest, remember you break your ratio if you divide one of them by a different number than the other. So they both have to be divided by the same number. We have 1 mole of carbon present for every 1.67 moles of hydrogen. So doubling doesn't help, but tripling does. I need to multiply all of these by 3. So I'm going to have C3H 1.67 times 3. That's 5. C3H5. So just do C1H 1.67, each of these times 3. And you get to a whole number. And so then the empirical formula weight of C3H5 is 12.01 times 3 plus 5 times 1.008. That's 41.07. So 164 divided by 41 is 4. So we got 4 of these units in one molecule. So we got 20 and 12. C12H12. You can double check. You can then say, well, what's the percent C and percent H of this? Let's do that real quick. 12 times 12 divided by 164, 87.8%. And that was kind of imprecise, but you can double check always at the end of the problem. All right, so that's the packet, and I will be posting this soon. Have a great test, everybody. Good luck on the exam.